A very welcome you all to the Ariser Talent. My name is Vibha Parekh and we are at the end of the chapter of some basic concepts of chemistry. And today already actually we have started the topic units of concentration, and today we are going to continue that particular topic. Okay. So, today our topic for the discussion will be units of concentration. So, I have already told you there are different types of units of concentration. We can use different ways in order to tell the concentration of a solution. So, yesterday as you might be remembering that I have told you that what a solution is, what a homogeneous mixture is, and how different concentrations are used in order to tell the amount of solute which is present into a amount of solvent, right, or in a solution. So, for that we have seen various kinds of units of concentration. Again I am going to give you a list of all the important units of concentrations. Okay. So, these are some of the units of concentration. Here we are not giving all, there are many actually units of concentrations, but what we are studying here for this topic is some of the important units, right. So, the first one is molarity. Second is molality. Third one is mole fraction. Fourth one that we will be studying today into the detail is percentage composition. And the final topic is parts per million. Okay. So, these are the 5 important units of concentration. Again and again I am saying this, that these are some of the important units of concentration, because it is not that these are only units of concentrations, we have more units of concentrations as well, but these are the concentration units which are used most of the time for the practical purposes. Okay. So, we have normality also, formality also, so there are lots of many of them. Okay. So, we have already discussed about this molarity, molality and mole fraction. So, before going to the percentage composition and parts per million, I am going to give you some of the highlights of these particular topics. We have already seen this. Okay. So, now for this topic we are going to see the formulas. Okay. As you must be remembering that what was molarity. Molarity was actually, and it was symbolized with a capital M, right. And molarity is what? Number of moles of solute present in liters of volume of solution. Okay. So, this was what the molarity of a solution. So, and when we have expanded the whole formula, then we have approached to a formula, ultimate formula, and that formula I am going to write over here. Okay. So, this is what, as we know that number of moles can be written as the weight of solute. So, I am writing weight or the given mass of the solute as W divided by capital M into which is the molar mass. Okay. Or in order to distinguish between these two, you can also write it as M. It is all up to you that what kind of symbolization you want to use. Okay. So, this M is the molar mass of the solute, then is multiplied by 1000, and here it is multiplied by volume if it is present in milliliter. And obviously, if it is present in liter as the definition says, then we need not to write this 1000 over here. Okay. So, this is the formula. Then for let us say for molality. Okay. So, for molality what we have seen, molality was represented with a small m. Okay. And here what we have seen, instead of volume which was given here, the solution was actually expressed in the form of volume or in liters or in milliliters, but instead of volume here we are going to see the mass of the solvent, right. So, this is W which is the given mass of the solute, then molar mass of the solute into 1000 multiplied by what? It is the mass of solution which is in grams. Okay. So, this is the formula that we have got for molality. Then we have the mole fraction. Okay. So, let us say I have a general equation like this, A plus B and this is giving us C. So, what does this small a, small b and small c are telling us? These are the stoichiometries of this particular chemical equation or in a balanced chemical equation, and A, B and C are the actual species. Okay. So, if this is the equation and let us say we have been told or we have been asked to find out the mole fraction of A. Okay. So, mole fraction is something which is not for the solution. Mole fraction is expressed or it is given for a particular species. Okay. So, if you are going to give a mole fraction of for A, then it will be like this. Mole fraction is expressed as X. So, for A, the mole fraction will be what? It will be number of moles of A divided by total number of moles present in a solution. Okay. So, number of moles of A, which we know as it is small a, okay, but still I am writing it like this, and we know this Na is actually this A, right. So, total number of moles of A number of moles of A divided by total number of moles which are present in a solution. So, it will be Na plus Nb plus Nc. So, these are the total number of moles that are present in a solution. Similarly, if you want to calculate mole fraction for any of the another species, like just for an example, if I want to calculate the mole fraction for C, okay, then in that case it will be equal to number of moles of C divided by total number of moles, right. So, this will be our equation. So, we have seen this part. These are the important formulas for molarity, molality and mole fraction. And one more thing that we have studied over here was about the dependence on the temperature, the dependence of these units of concentration on the temperature. Okay. In that case, what we have seen, in this particular case, we have seen that since molarity involves the solution in volume. Okay. So, let me first give you this over here. As we know that, what we know, we have a Charles law. Okay. You might not be knowing about this Charles law, but what does this Charles law says that V is directly proportional to temperature. It means that when the temperature increases, then volume automatically increases. So, these laws are applicable for gases, these are given for the gases, and obviously when we are talking about V in ml, so most of the time we are talking about either of the gases or of the liquids. Okay. So, it says that when the temperature increases, then volume automatically increases. So, V is directly proportional to T. So, this was given by Charles law, right. So, from what is the relevance of this particular thing over here? So, since we know that temperature and volume are directly proportional, and here what we see, here we can see that M is inversely proportional to volume. It means that as the volume of the solution increases, then the molarity of the solution decreases, and since we know that V is directly proportional to T, so here we will have a relation like this. Okay. So, it means that when the temperature increases, then volume increases, volume of the solution increases, but the molarity of the solution decreases. So, molarity and temperature are inversely related. Okay. So, this is T and this is M. So, M and T are inversely related, and this is all because we have volume of the solution given to us, right. But when we go to molality, in the case of molality, instead of volume of the solution, here we have mass of the solution. Okay. It is either given to us in the form of kilograms or into the form of grams. So, since we know that mass is not dependent on the temperature, mass is always constant. You must have studied many times into your physics book that the mass of a person on the earth is same as that of the mass of the person on the moon or on any other planet, because it is not dependent on anything. Mass is a constant term, it is not even dependent on the gravitational force. So, obviously, when it is a constant value, it is not going to change with that of the temperature. Okay. So, here since molarity sorry, not molarity, it is molality. Molality does not involve volume of the solution, that is why it is not even dependent on the temperature. So, what we say, because here we have mass of the solution which is independent of the temperature, and that is why we will say that molality is independent of the temperature. Molality is independent of the temperature, right. So, this is an important point, and again here we have a mole fraction. So, you can use your common sense, you can also obviously see over here that X is involving what, number of moles, and number of moles is actually what, it is a number. Okay, there is no variable, there is no such kind of thing which may vary with that of the temperature, because it is just a number, there are number of moles, we know this, right. So, if we have a concentration of solution, there must be some kind of number of moles, it is not going to change with any kind of temperature, pressure or any kind of conditions, right, because this is a number and number is divided by a number. So, obviously, we are going to get a number only into our result. So, since here we does not involve any kind of thing like mass or volume or any such kind of thing. So, obviously, this is also independent of temperature because it is a number. So, I think it is quite clear to you that since here we have number of moles which is a number. So, obviously, mole fraction is also independent of the temperature. Okay. So, by finishing 3 of these units of concentration, we have seen 3 formulas, and also we have seen the dependence of these particular units of concentration with that of the temperature. So, I think this is a very important point. This temperature relationship is very important, and you must always remember this, and you might be asked such kind of questions in indirect form, and you will have to be very conscious that the temperature, if the temperature something which is given in the form of the temperature, then you should understand this, that in which case temperature is going to affect the concentration and in which case it is not going to affect any of the concentration, right. So, I think this is quite clear. So, this was that part which we have already studied, and I have just revised you these particular 3 things. Now, moving on to the 4th unit of concentration, which is what, percentage composition. Okay. So, now we start our today's topic. So, it is what, it is percentage composition. So, the name itself is saying that what we are going to see over here. Okay. So, we have percentage composition. The next topic, which is the 4th one, right, and it is what, percentage composition So, again this percentage composition can be given in terms of the mass and in terms of the volume. So, obviously, it is telling us the percentage composition, it is quite clear, the name itself is self expressing, right. So, it is saying that how much percentage of a solute is present in a solution. Okay, and this percentage can be given in terms of the mass and in terms of the volume, as we have already seen in some of the topic like mass analysis and volume analysis, right. So, there also we have seen such kind of thing, but the difference over there and here is that here we are talking about the percentage composition. So, we have to give our value in under 100. Okay. So, let me give you a better explanation by this. So, this percentage composition can be given in 3 ways, as we have seen over there. So, these 3 are what? These 3 percentage compositions can be percentage weight by weight, or you can also write mass by mass. percentage weight by weight, okay. Then we have percentage weight by volume, and the third one that we have is the percentage volume by volume. So, it means that the one that is written over which is written above in the numerator part is actually telling us the weight of the solute, and the one which is written in the lower part or in the denominator is showing us about the weight of the solution, okay. So, this is the thing that you have to remember over here. Then we have weight over weight. So, let us first write a statement for this, okay. So, I am going to write individually the statements for all of them, okay. So, the first, the percentage weight by weight. So, here we have the percentage, or you may also write the mass, I think it would be much better, the mass of solute present in, since it is weight, so here we have to write 100 gram. It is percentage, that is why we are writing 100, and since it is weight, we are writing it as 100 gram. 100 gram of solution, okay. So, the mass of the solute which is present in 100 gram of the solution, mass of the solute which is present in 100 gram of the solution. So, this is what the percentage weight by weight. Now, for percentage weight by volume, we have the mass of solute present in, now it is also understood because here the solution is given in terms of volume, okay. So, here we have to write for the volume, we have a unit of liter or milliliters. So, here we will be writing it as 100 ml of solution, okay. So, the mass of the solute present in 100 ml of the solution, and here it was the mass of the solute which is present in 100 grams of the solution. So, okay. So, the third one is volume by volume. So, it is quite obvious. Now, here we have to write the volume of the solute. The volume of the solute present in 100 ml of the solution, okay. So, these are the three definitions that we have achieved from the percentage composition. So, the only thing that I think you should remember here is that here we have 100 gram of solution, here we have 100 ml, and it is also 100 ml of solution. Even you need not to remember this 100 gram or 100 ml because it is quite obvious from the formula as well, okay. So, if you have been given in your question that you have to find out the percentage weight by volume, it means it is understood that you have to write the value in 100 ml, right. So, I think this is okay. Now, we are going to see the formulas of all the three percentage compositions, okay. So, now let us see the formulas. Now, since you know the statement or the definitions, you can easily make your own formulas, right. So, the first one that we have, so let us say the first one I have is the percentage weight by weight, okay. So, the percentage weight by weight is equal to mass of solute divided by mass of solution into 100. Is this okay? Then we have second formula which is for percentage weight by volume, okay. So, percentage weight by volume will be equal to mass of solute present in volume of solution, into 100, and the third one we have is the volume by volume. Okay. So, the formula for it will be volume by volume, which will be equal to volume of solute present in volume of solution into 100. Okay. So, these are the three formulas, and you have to remember here that again and again we are using the word solution. Here I have not used the word solvent. We know this, right, that solution is different from solvent. How is this different? Because we know this thing, that a solution is made up of what? It is solute plus solvent. Okay. So, let us say if I have an example, I am just giving you an example, like I have a beaker, okay, and I have been given, let us say 100 ml of water. Okay. So, here I have what? I have 100 ml of water, and let us say I have been given 10 gram or 10 gram or 5 gram of salt. Okay, the same salt that we use at our homes, which is the table salt. So, let us say I have been given that 5 gram of salt, okay, and I have been told to dissolve that 5 gram of salt into that of 100 ml of water. Okay. So, here I have, this is what? This is salt, and let us say this is how much? This is 5 grams. Since the thing which is present in lesser amount is considered as the solute. Okay. So, here as we can see, it is 100 ml, but this is 5 grams. So, obviously 100 ml is much more than that of 5 gram. 5 gram is very little quantity. So, this 5 gram which is present in lesser amount is known as the solute. So, what is solute? So, here we can say that salt is a solute, but this water is a solvent. Okay. So, I hope you know the difference between a solution and the solvent. When this solute and solvent mix together and dissolve, the solute is completely dissolved into the solvent, then it is told as a solution. Okay. And then also we have two types of categories, whether it is a homogeneous solution or a heterogeneous solution. So, let us say if our solute is getting completely dissolved into the solvent, then it will be called as a homogeneous solution. Okay. So, there we are talking about the mass of the solution. Here I have not written as the mass of the solvent. So, let us say if you have been given such kind of condition. So, it is 5 gram and this is 100 ml. Okay. This one is 5 gram and this is 100 ml. So, this will be an this will be an example of percentage weight by volume. Okay. So, the weight of the solute, which is the mass of the solute, will become 5 gram and the volume of the solution will become, then you will have to see that how to calculate that volume of the solution. So, I am going to give you an example, and with that I hope you will be more clear to your concepts, right. So, this is an example of percentage weight by volume. So, let us take an example. So, I am just taking an example of weight by volume. Okay. So, that will make you more clear that how to use these formulas into the numericals. Okay. So, let us say I have an example in which I have been said that 0.5 gram of solute is dissolved in let us say 75 ml of water. Find percent weight by weight, or let us say it don't, because I have written this formula weight by weight. So, I am putting this as gram. Okay. So, it will be more convenient for you to understand, since here I have written the formula of weight by weight. Okay. So, here the value is in 0.5 grams, and again the solvent that is given to us is present in grams. Okay. Now, what you have to do, just substitute these values into the formula. So, the mass, the percent weight by weight will be how much? Mass of the solute. So, here we have a solute which is having a mass of 0.5 gram. So, this is how much? 0.5 gram divided by, now here we have mass of the solution. It means that you does not have to directly write 75 grams over here. It is a solution, but water is a solvent, the same thing that I have told you. So, what you have to do here? Now, you have to write the total mass of the solution. So, the total mass of the solution will be containing 75 gram as well as 0.5 gram, right. So, this will become 0.5 plus 75 gram. Okay. Now, you can make your calculations. So, this will be how much? 75.5 gram. Now, I hope you can make this calculation. Whatever will be the answer will be the percentage, and also you have to multiply this with 100. Here also you have to multiply this with 100. So, whatever will be your answer will be the percentage weight by weight of the solute in 75 gram of solution. Okay. So, I think this is fine. So, we have completed this topic of percentage composition. Now, let us move to the another topic, which is parts per million. Now, the last unit of concentration is parts per million. So, this is the fifth one, okay, parts per million. So, the parts per million is what? So, first of all, I would like to tell you that parts per million is a unit of concentration which is used for those solutions in which the solute amount is quite very less. Okay. So, such kind of very dilute solutions are called are expressed in terms of parts per million. So, this is the first thing that you have to remember for parts per million. And is it having a word of million? We know that how much a million is a term which is equal to 10 to the power 6. Okay. So, the parts per million means how much part of the solute is present in 10 to the 6 power part of our solution. This is what parts per million is. Okay. So, again, so since we know that what is a parts per million, again I would like to tell you that this parts per million can be expressed in terms of two things. The first one is according to moles, or the second one is according to mass. Okay. You can discuss the parts of the solute in a solution in terms of the moles, 10 to the power 6 number of moles or 10 to the power 6 mass, which can be gram or kilogram. So, kilogram is a huge quantity. So, I think gram will be fine, right. So, this can be expressed in terms of mass and moles. But let us say if you are not given anything, you have been just written that 10 ppm. If nothing is given to you, 10 ppm per mole is not given to you, in that case by default you are going to consider the mass of ppm. Okay. So, now let us find the formulas for moles and mass. Okay. So, let us first write the definition for parts per million. So, what is the parts per million? The definition will be, or the statement for parts per million will be, the parts of, or you can also say instead of parts, or here in the bracket I am writing the moles or mass. Okay. So, this part can be expressed in terms of moles or mass. So, the parts of solute present in every 10 to the power 6 or we can say millionth. Okay, 10 to the power 6 parts of the solvent is known as the parts per million of solute. Okay. So, here we have got this. So, the parts of the solute present in every 10 to the power 6 parts of the solvent or solution, I think right, solvent solution, is known as the parts per million for the solute. Okay. So, you might have read this in many a times in the newspaper or in the on the channels, let us say on the TV channels, that 10, let us say 30 ppm, 0.33 pm, 30 pm or 30 pm, you can use anything, of Hg is found in this water body, in this water body. So, as we know that Hg is what? Hg is a, so you can also write it as 30. Okay. So, let us say Hg, we know that Hg, cadmium, mercury, then nickel, all these are the heavy elements. Okay. You should also know this, that this is a heavy element. So, 30 ppm of heavy element is present in the water body, in so water body. Okay. So, what is this heavy element and what is this 30 ppm is saying? So, it means that 30 parts, so I have told you if nothing is written over there, then you have to consider the mass. So, it means that 30 gram of Hg is present in how much? 10 to the power 6. So, there will be 6 zeros of water. In every 10 to the power 6th gram of water, we have 30 gram of mercury. So, since this is very less quantity of solute, so instead of writing this concentration in terms of molarity or mole fraction, we are more interested in using a different unit of concentration, and that is why we use ppm for this. Okay. So, I think it is quite fine. So, let us write down the formula. Okay. So, the formula for ppm is what? So, the formula for ppm, which is parts per million, is equal to mass of solute divided by total mass into 10 to the power 6. Earlier when we were calculating the percentage composition, we were multiplying this part with that of 100, because there we were expressing our amount of substance, amount of solute in terms of percentage. So, there we were using 100, but since now we have per million value, that is why we are multiplying this with 10 to the power 6. Okay. So, this is quite simple. So, similarly, if you are given the moles of solute, you will write here the moles of solute divided by total moles into 10 to the power 6, and by default, as I have said, anything, if nothing is written over there, then you have to write the mass. So, the mass of the solute divided by total mass into 10 to the power 6. Okay. So, for this is for mass, and for moles this will be what? Moles of solute divided by total moles into 10 to the power 6. Okay. Is this fine? Okay. Now, then moving on to the next topic, which is what? Equivalent weight. So, this is also something which is quite common in use. You might have most of the time seen the equivalent weights. Okay. So, in a very quick way, we are going through the equivalent weight. So, it is quite simple. First of all, write down this equivalent weight in general is what? It is the molecular or atomic weight, whatever is applicable, divided by the valence factor. Okay. So, we will see with an example that what a valence factor is. So, basically you need to remember this, that equivalent weight is molecular or atomic weight, whatever is applicable, divided by the valence factor. Okay. So, where in what cases you can see the equivalent weights? So, you can see equivalent weights in case of let us say ions, for salts, then you can see them for acids or bases, and you can also see them for oxidizing or reducing agents. Okay. So, you can see this. Now, what will be the subsequent formulas for these particular things? So, you may see that equivalent weight, it will be equal to, for ions, it will be equal to the weight of ions or the mass of ions, or you can also write the formula weight. Okay. Formula weight divided by the valency. Okay. So, whatever is the charge which is present over the ion, or you can also write the charge, okay, or the charge on ion. So, this is the same thing. Then we have the salt. So, salt is containing a cationic part and an anionic part. Okay. So, for this the equivalent weight will be the formula weight instead of writing this as the formula weight, this will be more appropriate to write the weight of ion. Okay. So, here we have writing formula weight is generally used for the salts or for the ionic compounds. That is why I have written, I have erased that formula weight and I have written it here. Okay. So, this is the formula weight and the total charge present on cation or anion. Now, for acids and bases, this is same. Okay, all the formulas are same, but according to our species we are going to decide the valencies, valence factors, right. So, for acids and bases, what we have is the molecular mass divided by acidity or basicity. Okay. So, if we have an acid, we will be writing it as the molecular mass of the acid, and if it is a base, then we will be writing the molecular mass of the base divided by basicity. Okay. So, then we have oxidizing and reducing agents. So, again we will be writing the molecular mass, and since we know, you must be knowing that what an oxidizing agent is and what a reducing agent is. So, we know that oxidizing agents are those which oxidizes others and reduce itself. Okay. So, these are the agents which reduces itself and oxidizes others. So, in short, we may say that oxidizing agents are those which gain electrons. Okay. And what are reducing agents? Reducing agents are those which reduces others and oxidizes, reducing agents are those which reduces others and oxidizes itself. So, it reduces others and oxidizes itself, or in short we may say that they lose electrons. Okay. So, we are going to write the same valence factor over there. So, if it is an oxidizing agent, we know that it is going to gain electron, number of electron gain or electron lose. Okay. So, if we have an oxidizing agent, we will be writing the molecular mass of the oxidizing agent divided by the number of electrons gained, and if it is an reducing agent, then the equivalent weight will be equal to the molecular mass of the reducing agent divided by the number of electrons lost. Okay. So, according to the species with which we are dealing with, we are going to write the formulas for the equivalent weight. Okay. So, I think this is quite fine, and now I am going to give you an example so that it will become more clear to you. Okay. So, let us see an example. So, here we have the valence factor. Okay. So, let us say if I have an example of H2SO4. We know that H2SO4 is what? It is a acid, sulfuric acid. Okay. So, if we want to find the equivalent weight for H2SO4, so how to find this equivalent weight? Okay. So, I am writing EQW2 WT as the equivalent weight. So, we know that H2SO4 when breaks it will form 2H plus SO4 2 negative. Okay. So, now what we have to write? The molecular weight of the H2SO4. So, we know that how to calculate the molecular weight. So, here we have 2 hydrogens and the weight of one particular atom of hydrogen or 1 mole of hydrogen atom is how much? 1. So, this will be 2 into 1 plus 1 sulfur. So, the weight for sulfur is 32, and since we have 1 atom of sulfur, so I am writing it as 1 plus oxygen is 16 into 4, okay, divided by, so how many electrons are actually being taking participate into this reaction. So, since we know that for here if we take the take an example of the cation, we can easily see that here we have 2 plus ions and there also we have 2 electrons. Okay. So, the total charge we have that is actually participating into the reaction is 2. Okay. So, this will be equal to 2. So, this is how you have to decide about the valence factor. Okay. Now, what you have to do? Simply calculate this. So, this will be 2 plus 32 and plus 64 divided by 2. So, this will be equal to 8, 98 by 2 and this will be equal to 49. Okay. So, as we know that the molecular weight for H2SO4 is 98. Molecular weight for H2SO4 is 98, but the equivalent weight for H2SO4 will be 98 by 2, which will be equal to 49. So, this is how you are going to calculate the equivalent weights for any kind of substance depending on the behavior of the thing which with you are dealing with. Okay. So, with this we are we have completed the topic of equivalent weight and different types of units of concentration. So, I hope that it was simple and we have also seen some of the examples. So, I think this is quite okay for today's lecture. Thank you so much. Have a nice day.